Dr. J. Kamala received her BE in Electronics and Communication Engineering from Madurai Kamaraj University in 1989, ME in VLSI Design from Bharatdasan University in 2002, and PhD from Anna University in 2011. She is currently working as Associate Professor in the Department of Electronics and Communication Engineering, Anna University, Chennai. Her research interest includes VLSI design, solar power, controller design, and smart sensors. She has published several papers at national and international journals.
Welcome to the UGC lecture series on agricultural engineering. Today we are seeing about renewable energy part 8. In this part we are going to see about solar refrigeration systems. As the environment is going hotter day by day, we need the equipments for cooling applications. Here nowadays more people are using air conditioning and refrigerator for lot of applications. Some areas of the world they are using heating applications because already they are so cool, that environment is so cool, so they are going for cooling applications. Now we are seeing about solar refrigeration. The refrigeration is a process in which work is done to move heat from one place to another place, and it is having different types. We are having solar power electrically generated and solar thermal energy generated solar refrigeration. More number of types are there. If we see solar power electrically driven, we are having PV operated and solar thermal energy generated solar refrigeration. If we see about solar energy refrigeration using thermal energy, there we are having different types: absorption type, adsorption type, solid dissident, liquid dissident, like that lot of types are there. Here we are going to see about only major 3 types of solar refrigeration. The first one is photovoltaic operated refrigeration system. The photovoltaic panels are used to convert sun energy or sun radiation into electrical energy. So this refrigeration uses electricity from the PV panels to operate the refrigeration system. Next one is solar mechanical refrigeration. Here solar thermal energy is used to have some mechanical work. This mechanical energy is again converted to produce cooling effect. This is solar mechanical refrigeration. And next one is absorption refrigeration. Here some of the materials are used by a pump and it uses low power compared to solar mechanical refrigeration. This one uses very less power and it uses a pump and the absorption property of some materials for cooling applications. These are the 3 major types of solar refrigeration system that we are going to see in this webinar lecture. So first we see about solar refrigeration. It includes both photovoltaic or solar thermal energy. We can use either photovoltaic effect or thermal effect. In case of photovoltaic based solar refrigeration system, they use low voltage DC compressors. The PV panels, if we see, they convert the solar energy into electrical energy. That electrical energy is in the form of direct current. We derive only direct current from the PV panels. So DC compressors and DC motors are used in the PV operated solar refrigeration, and the DC compressors and motors are also is of low voltage, about 12 volt or 24 volt based DC compressors and motors are used. And when they are using this type of refrigeration, higher levels of insulation around the storage compartments are used to maximize the energy efficiency. They use higher levels of insulation around the storage compartment, because if the insulation is not there means the thermal energy will get dissipated from the storage compartment. So, they are using higher levels of insulation around the storage compartments. It can be used for 10 to 85 liters of storing vaccines. We need the important medical application of storage of vaccines, because some of the vaccines are to be stored at lower temperature. So, we can build solar refrigeration units to store 10 and 85 liters of vaccine storage capacity with ice production rates of up to 6.4 kilogram per 24 hours. In a day we can produce up to 6.4 kilogram. Next, the basic block of photovoltaic operator refrigeration systems includes a solar panel. This solar panel receives sun radiation and produces direct current. We will be having a positive terminal and a negative terminal. The output of the solar panel is not constant. We do not get regulated output from the solar panel. If the period, if the day, the period during which we are operating, if it is sunny means we get more power. If it is not sunny, or if it is clouded, or some birds are going across the panel, or any obstruction is there, or we have passing clouds, in that case any shade, in that case the output power is reduced. The output of the solar panel is not constant, it is always varying. So, we need a controller so that we get a regulated output from the solar panel, because the compressors, motors and other electrical equipments we are using require a constant supply of voltage or current. In that case we need controllers. So, this controller will perform the operation of all the optimization techniques to derive maximum power from the solar panel. It includes maximum power point tracker circuit and algorithm. So, it will derive maximum power from the solar panel, and it regulates the output voltage and current of solar panel is always varying, and it makes it constant, and it makes the output voltage and current compatible to other electrical devices connected in the system. If we use a 12 volt battery, the panel output is regulated to 12 volt. If we use 24 volt battery, the output voltage will be regulated to 24 volt. And again the battery is used to supply the refrigeration during night times and cloudy times. According to the period of operation or period of non-sunny period, we have to design the battery. If we want to have backup for 3 or 4 days, higher capacity battery is to be used. If we want for very less period, if it is not cloudy on the subsequent days and we will get always sunny means only night time alone we use battery. So, that time we can use lower capacity battery. And the equipments inside the refrigeration, the compressors and other electrical equipments in the refrigerator are controlled by the controller. So, the purpose of the controller is to smooth the output. The voltage output of the panel is not constant, it is varying always. So, it is smoothened by a capacitor, and during starting operation of the compressor, it takes more current or more power. During that time, it will support by from the battery, it can take more current and switch on the compressor. Once the compressor is switched on, afterwards the compressor does not require more power. In that case, it during startup operation, the controller supports additional current for starting up of compressor. And the next one is monitoring the rate of change of regulated power, whether the compressor is operating below the maximum power or above it, because the compressor should and other electrical equipment should be operated below the power rating of the electrical equipments. If it is operated above the rating, it will lead to hazards like fire in the electrical equipments. More heat will be generated. To avoid it, the controller monitors the rate of change of regulated power, and it always regulates the power to the compressor, battery and other electrical equipments connected in the system. And replacing the capillary tube in the refrigerator system with an expansion valve. The capillary tube in the refrigerator system is replaced with the expansion valve. This improves energy efficiency in certain operating conditions. So, these are the functions of the controller, and the basic block includes a solar panel, controller, battery and a refrigerator. Inside the refrigerator, we will be having more number of units to function the refrigerative unit. Here, this is the refrigeration unit. We will be having a motor, DC motor, because we are getting a DC output from the PV panel, a DC motor, it is attached with a compressor, and we will be having a refrigerated chamber and condenser and expansion valve. So, this is the refrigerative unit. Here the motor and compressor are operated by the PV panel, vapor compressor, thermal storage, reservoir and electronic controls are the basic building blocks of the PV operated refrigeration system. The DC electrical power drives the compressor to circulate the refrigerant through a vapor compression refrigeration loop. It extracts heat from the insulated enclosure. The enclosure includes thermal reservoir and a phase change material. This phase change material freezes as heat is extracted from the enclosure and creates an ice pack. So, whenever the material freezes, the heat is extracted from the insulated enclosure and it creates the ice pack. It enables temperature maintenance inside the enclosure in the absence of sunlight also. So, these are the blocks inside the PV operated refrigeration system. We will be having a controller unit and PV panel unit fitted outside this refrigeration system. The controller will supply a constant voltage to the motor and the compressor, and this includes a heat transfer process which creates ice and cooling effect in the refrigeration system. The battery is used to provide DC power to the motor and compressor when solar power output is not available. These are the building blocks inside the refrigeration system, PV operated refrigeration system. And conversion of solar power into thermal energy for storage. It could be maximized by two methods. One is proper sizing of highly insulated cabinet. The highly insulated chamber is to be sized properly. And phase change thermal storage. What should be the size of thermal phase change thermal storage? Variable speed compressor, solar PV panel. The size, what is the capacity of solar PV panel, wattage, those things are to be sized properly. These are all very important for maximizing the conversion of solar power into thermal energy. Next one is compressor control. It is designed to fully exploit the available energy. We have to design compressor, the insulated cabin, phase change thermal storage and other solar panels, so that we can optimize the solar power into thermal energy conversion. Applications of PV operated refrigeration system are, it can be used to cool, have cold side water loop or incorporation of the evaporator into the thermal storage. These are the PV operated refrigeration system operating principle and the applications. Next one is solar mechanical refrigeration. Here it uses thermal collector. A solar collector is used. This one converts the solar sun radiation into heat. So, solar collector converts the sun radiation into heat. This heat is used for the boiler, and this boiler is attached with condenser, pump and expander. Here mechanical work is achieved in this block. From this the mechanical work is transferred into cooling effect again by a expander and expander. This is solar mechanical refrigeration, where mechanical energy is converted into electrical energy. So, it uses a conventional vapor compression system driven by mechanical power. It is produced with a solar driven heat power cycle. Most of the solar mechanical refrigerations are operating based on vapor compression cycle principle. The heat power cycle usually considered for this application is a Rankine cycle. Rankine cycle is a thermodynamic cycle. It is used to convert the mechanical energy into cooling for cooling effect. That is called Rankine cycle. It is a thermodynamic cycle. Then here in the previous one, they are using a compressor for the solar mechanical refrigeration system. Here another one is ejector based. In the solar mechanical refrigeration system, two types are there. One is Rankine cycle based solar refrigeration system and another one is ejector based solar mechanical refrigeration system. This diagram uses one ejector. So, it uses ejector in place of compressor. Here also solar collectors are used to convert the sun radiation into heat. This heat is used in the boiler. A pump is used. The pump used in this system consume very less power compared with the previous Rankine cycle based solar mechanical refrigeration, and we will be having a condenser and evaporator with a ejector to get the cooling effect. And for this case, the fluid is vaporized at an elevated temperature by heat exchanger with fluid heated by solar collectors, and storage tank can be included to provide some high temperature thermal storage. The vapor flows through the turbine or piston expander to produce mechanical power. The whatever vapor flows through the turbine, it produces mechanical power. The fluid exiting the expander is condensed and pumped back to the boiler pressure, where it is again vaporized. The efficiency of this Rankine cycle increases with the increasing temperature of the vaporized fluid entering the expander. The efficiency of the solar collector, however, decreases with the increasing temperature of the delivered energy. So, if we see compare the efficiency of Rankine cycle and the efficiency of solar collector, only either one can have more efficiency. If we increase the efficiency of Rankine cycle, the efficiency of solar collector will be reduced. If the efficiency of solar collector is increased, the efficiency of Rankine cycle will be reduced. So, we have to compromise with both Rankine cycle and solar collector efficiency. So, we can go for high temperature by using concentrating solar collectors that track the sun position. The solar collector is tracking always the sun, because in the morning the sun position is different, afternoon the sun position is different, and in the evening the sun position are different. So, according to the sun position, we can track the solar collectors in one dimension or two dimensions, so that we get maximum energy from the solar panel. But the problem with the tracking system is it adds cost to the system. More controllers are required, more equipments will be added. So, weight is also added and complexity is also increased in the system. So, tracking system is not advisable in real time applications. So, they are going for tubular, evacuated tubular, compound parabolic or advanced multi-cover flat plate collectors. Different types of collectors like evacuated tubular, compound parabolic or advanced multi-cover flat plate collectors could be used to produce fluid temperatures ranging from 100 degrees centigrade to 200 degrees centigrade. This is another method of increasing solar collector efficiency. So, this solar mechanical refrigeration, the efficiency of the solar collector depends on both solar radiation and difference in temperature between the entering fluid and the ambient temperature. The overall efficiency of the solar refrigeration system is the ratio of mechanical energy produced to the incident light radiation, solar radiation, or it can be represented as a product of efficiencies of solar collector and the power cycle. This is an important parameter of the solar mechanical refrigeration system, and we want to improve the efficiency. Because of the competing effects with the temperature, there is an optimum efficiency at any solar radiation. The solar mechanical systems are competitive only at higher temperatures, for which tracking solar collectors are required. Because of this economy of scale, it is applicable for large refrigeration systems like, for example, 1000 tons or 3517 kilowatt temperature. To reach for large scale application only, we will be going for solar mechanical refrigeration. Next type of refrigeration we are going to see is absorption refrigeration. It is a heat driven system. It requires minimal mechanical power for the compression process. It replaces energy intensive compression in a vapor compression system with a heat activated thermal compression system. So, instead of having a energy intensive compression, it will be having a thermal compression system, and it is also activated by heat. This absorption cooling system uses lithium bromide water absorption refrigerant. The working fluids cannot be used at temperatures below 0 degree centigrade. Instead of the compressor, it uses a series of 3 heat exchangers. The exchangers are absorber, regenerating intermediate heat exchanger and generator. So, instead of compressor, it uses these 3 heat exchangers: absorber, regenerating intermediate heat exchanger and generator, and a small solution pump. This pump consume very less power compared to previous 2 types of refrigeration systems. This is the block diagram of the absorption refrigeration system. We will be having one evaporator, absorber, heater, generator and condenser. We will be getting the cooling effect from the condenser, and the operation is represented in different states from 1 to 7. If we see the operation, the ammonia vapor exiting the evaporator, the ammonia vapor is applied to the evaporator and it is exiting at 6. State 6 is showing the ammonia vapor exiting the evaporator. It is absorbed in a liquid solution of water ammonia in the absorber. It is absorbed in the absorber. The cooling water is required to carry away the heat in this process. We will be having the ammonia rich liquid solution from the absorber, that is state 7, that is this here. From the absorber, we will be getting ammonia rich liquid solution. It is pumped by a pump to a higher pressure through a heat exchanger. This is a heat exchanger. Through the heat exchanger, it is pumped and delivered to the generator. This is the generator, that is state 1. Ammonia enters the evaporator, gets evaporated and absorbed. Again it is pumped into a high pressure generator. In the generator, the liquid solution is heated, which promotes desorption of the refrigerant from the solution, and from the generator it is applied to the condenser and we get the cooling effect from the condenser. So, in this block diagram, ammonia is entering the evaporator, it is absorbed in the absorber, again it is pumped to generator through the heat exchanger. From the heat exchanger, the liquid solution in the generator, the liquid solution is heated, which promote desorption of the refrigerant from the solution, and it is applied to the condenser. The condenser produces the cooling effect. This absorption type refrigeration uses minimum power compared with the previous 2 types because it replaces the compressor with 3 element: absorber, evaporator and heat exchanger, and a small pump. It consumes very less power, so it is advantageous compared to the previous types of refrigerations. And the applications of the solar refrigeration systems, if we see, it could be used for household and commercial indoor cooling purpose. The refrigeration in off-grid rural areas, where the places where grid is not available, power is not available, there we can use it to preserve the food and vaccine. It is used in cold storage system to prevent rotten prone food, used to make ice cream and other related products, as the application or requirement for refrigeration is increasing day by day, and this solar refrigeration system is very needful and important application nowadays in the present environmental conditions. And cooling purpose for transportation vehicles, e-vehicles we are having, there for cooling purpose we can use the solar refrigeration system. These are the applications of solar refrigeration system. With this we have seen different types of solar refrigeration system, its basic principle and the applications. Thank you.